Salam and welcome everyone. So today we're going to be working on the question on the screen that says calculate the maximum non-expansion work per mole of CH4 that may be obtained from a fuel cell in which the chemical reaction is the combustion of methane under standard conditions at 298 kelvins. It's very important for you to know that whenever you're asked to find a question like this, the maximum non-expansion work, and you also hear under standard conditions, know that the work that you're talking about is just simply equal to the Gibbs energy of reaction. So that is basically what you're supposed to use. So you're going to use your knowledge of the Gibbs energy of reaction to actually solve this question. This is how it works. All of this information that you're telling you, this is just to like put more like just basically jumble up. They could as well just ask you to find the they could as well just ask you to calculate the Gibbs energy of reaction for the combustion of methane, and that's just it. That's literally what you're asking you to do. But this way they said work per mole. So it's just basically this. So understand that under standard conditions where the pressure and the temperature, and now you're hearing non-expansion and the volume is unchanging, notes that the non-expansion work per mole is equivalent or equal to the Gibbs energy of reaction. So we know the general formula for the Gibbs energy of reaction, okay, to be the summation, okay, of the Gibbs energy of formation, okay, for the product, okay, minus the Gibbs energy of formation for the reactants. So that's basically how it's done. That's basically the formula that we're going to be using. And we're also told that of CH4 that may be obtained, calculate the maximum non-expansion work per mole. Okay, we know that of CH4 that may be obtained from a fuel cell in which the chemical reaction is the combustion of methane. So combustion reaction is just the reaction between whatever we're given, in this case CH4, okay, we're going to react it with oxygen to get or to form carbon dioxide gas and water. So H2O liquid. So that's basically how it's done. So CH4, of course, is a gas, methane gas. Oxygen is also a gas. So we're going to balance this chemical equation. And when we balance it, we see that we have to balance the hydrogen. We've already balanced the carbon, but we have to balance the oxygen. So you have this is the balanced chemical equation. So from this information right here, we can start working. We're gonna first of all organize this reaction according to the formula up top, where we focus on the Gibbs energy of reaction. So we're gonna first of all work on the products where we know that the formation, okay, the Gibbs energy of formation of the first product here is CO2 gas. Okay, so that's basically this one right here. Plus the Gibbs, because of course the summation information is saying we're going to add them up. So for all of the products first. So the Gibbs energy of formation for the second product, which is 2H2O liquid, minus now we focus on the reactant, where we have the Gibbs energy of formation for the first reactant, which is CH4 gas, plus the Gibbs energy of formation for the second reactant, which we know to be 2O2 gas. Now, I want to quickly mention something very important. You see this V here and this V here, they represent the coefficient of the products and reactants compounds. So in this case, we have the coefficient for CH4 to be 1, the coefficient for CO2 to be 1, but we have the coefficient for both O2 gas as well as H2O liquid to be 2. So we have to put that into consideration, meaning we're going to have to rewrite our formula in order for us to take those that information into account. The Gibbs energy of reaction becomes okay 2 sorry. So the Gibbs energy of reaction becomes change the Gibbs energy of formation for CO2. We're going to rewrite this one again because of course that's not the stuff that has the coefficient. So plus 2 times the Gibbs energy of formation for H2O liquid. So what we're actually just redoing here is to take into account all of this all of the coefficient. That's all we're redoing. We're just taking into account all of the coefficient. So yeah, so minus, we do the same thing here. This one has no coefficient greater than 1, so we don't have to say 1 times. We can just rewrite it. So you have the Gibbs energy of formation, okay, for CH4 gas, okay, plus the Gibbs energy of formation of 2CO2 would just be 2, okay, times the Gibbs energy of formation of O2 gas. So this is basically how it's done. So that's basically how you do this. So of course, now we can comfortably substitute. For those of you who don't know, I'm going to be using the resource section of my physical chemistry textbook, and that is basically how I'm going to be able to like solve this. So the resource section of the physical chemistry book has all of the standard um gives energy or formation for all of the compounds. So you make sure you like look at it. But for anybody who doesn't have their textbook handy, let me just write all of that information for you. So the Gibbs energy of formation would for all of them would be this. So now that I've successfully written all of it, we can just simply substitute. So, but make sure that like you always have your textbook handy just in case of next time or in case you have another question that you have to do. So you have CO2 for the one for gas, you have negative 394.36, okay, kilojoule per mole, okay, plus 2 times the one for water is just negative 237.13 kilojoule per mole, okay, minus, so we're gonna do the one for CH4. So minus the Gibbs energy of formation for CH4. We know that to be simply negative 50.72 kilojoule per mole plus 2 times the Gibbs energy of formation for O2 gas will just simply be 2 times 0 because that's what we have here. So 0 kilojoule per mole. Of course, now we have all of this information. We can just do the math. So the Gibbs energy of reaction becomes negative 394.36 kilojoule per mole, okay, minus 474.26 kilojoule per mole. And then here you've got minus and then minus again. So minus minus will give you plus. So this would be plus 50.72 kilojoule per mole. So plus 2 times 0 is 0, so you don't have to write plus 0. So you can just basically input all of this information in your calculator. You have negative 394.36 minus 474.26 plus 50.72. So that's going to simply gives energy of reaction becomes negative 868.62 kilojoule per mole plus 50.72 kilojoule per mole. So the Gibbs energy of reaction becomes negative 868.62 plus 50.72 would give you negative 817.90 kilojoule per mole. And as you're aware, in chemistry, anytime we're done with the calculation, we have to make sure that we're putting the right number of sig figs or decimal places. And you know, we're dealing with additions here, so we're going to focus on decimal places. We see that this first information, we have two decimal places, two decimal places, two decimal places, and we're supposed to pick the lowest number of decimal places according to the decimal places rule in calculations, especially in chemistry. So we have our answer in two decimal places. So our actual answer is just basically what we got. I want to quickly mention something so there's no confusion. I saw in some calculations online that people are given the absolute value of negative 817.90 kilojoule per mole, and they're turning that negative to positive. So I know a bunch of students can watch this video. I am a chemistry major, physical chemistry major. I'm sorry, chemistry. I'm done with university, but I studied chemistry, pure chemistry in college. I know that there are other students in engineering and physics that may be doing it. So I don't know, maybe it's a difference in the course of study that you're doing where you're maybe required to use absolute values. But for this question, I'm just going to give it the pure value, which is just basically negative 817.90. Make sure you ask your teacher for more understanding. So like I said, make sure you ask your professor. I think part of the reason why people are using the value though personally is because they're asked to calculate the maximum non-expansion work per mole because it's a non-expansion work and the reaction is basically what is creating the work like through the fuel cell. Maybe that's the reason why our value is negative because work is negative when the system is doing the work and it's positive when the surroundings is doing the work. So the pure value is negative, but the reason why maybe they're putting the absolute value is because they want to be able to say this amount of work was done, not necessarily. And when you say this amount of work was done, you don't put a negative there, you leave it, you make it a positive. But if you're just talking about the pure value, like in this case, it's a negative. But don't rely on just what I've said. Please ask your physical chemistry professor and do more research. I wish you guys all the very best. If you're a student who is struggling in any of your STEM related courses and you're trying to succeed, make sure you email me at shohabitutoring@gmail.com. I help students in middle school, high school, or college succeed and be the best version of themselves in their academic career. So email me at shohabitutoring@gmail.com to know about my tutoring and mentorship services. I wish you guys all the best. Assalamu alaikum wa rahmatullahi wa barakatuh.